All right, today we're going to zoom way in, down to the atomic level. We're going to talk about one of the most fundamental forces in the entire universe, chemical bonding. It's basically the invisible glue that holds, well, everything together, and we're about to figure out exactly how it works.
So, take a look at this. What you're seeing is a model of a molecule. It's this super complex arrangement of atoms all stuck together. And these kinds of intricate structures, they're the building blocks of literally everything, from the water you drink to the very DNA that makes you, you.
And that really leads to the big question, doesn't it? What is this invisible force that holds all this stuff together? I mean, why don't atoms just float around on their own? Let's break it down.
So here's our game plan. First, we'll look at the social life of atoms, why they even bother to bond. Then we'll define what a chemical bond actually is. And after that, we'll explore the three main ways they do it: sharing, giving and taking, or creating this kind of crazy sea of electrons.
Okay, so first up, the social life of atoms. And you can kind of think of it this way. For most atoms, being single is actually a really high-stress situation.
So here's the deal. A lone atom, just by itself, is usually buzzing with a whole lot of potential energy. A good way to picture it is like a tightly wound-up spring. It's just unstable and waiting for a chance to release all that pent-up energy.
And this gets at a really fundamental rule of the universe. Nature is, well, kind of lazy. It always prefers the lowest, most stable energy state it can find. So that high-energy, unstable atom, it needs to find a way to just chill out. And it does that by partnering up.
And that brings us to the perfect solution for an atom's little stress problem, the chemical bond. This is exactly how atoms get to that calm, low-energy state they're constantly looking for. Okay, so here's the official textbook definition. A chemical bond isn't really glue. It's a mutual electrical attraction. You've got this pull between the positive core of one atom, its nucleus, and the outermost electrons, we call those valence electrons, of another atom. That mutual pull, that's the force that binds them together.
In this visual right here, this really shows you the why of it all. See, on the left, you've got that lonely, high-energy, unstable atom. But on the right, after bonding, the atoms have managed to lower their potential energy, and now they're stable. That constant drive towards stability is the engine behind pretty much all chemical reactions.
But here's the thing. Atoms have a few different strategies for bonding, and it all comes down to how they decide to rearrange their outermost electrons. So let's take a look at the first approach.
First up, we've got the sharers of the atomic world. These are covalent bonds, and this is a really collaborative, cooperative way to get stable.
The key idea here, the absolute most important word to remember, is sharing. In a covalent bond, you have two atoms that basically agree to share one or more pairs of their electrons. Nobody gives anything up for good, they just cooperate.
So this sharing means the electrons are pretty much co-owned by both atoms. This type of bond usually happens between non-metal atoms, and it's what creates these distinct little units we call molecules. A perfect example is H2O, water, right? That's two hydrogen atoms and one oxygen atom all sharing electrons to stick together and be stable.
All right, now let's talk about a totally different strategy. If covalent bonds are all about cooperation and sharing, then ionic bonds are, well, they're more like a transaction. So let's meet the givers and the takers.
So instead of sharing, this bond is all about a complete transfer of electrons. You've got one atom that gives and another that takes. This whole process creates atoms with an electrical charge. We call them ions, and, as you probably know, opposites attract.
Okay, so here's how it plays out, step by step. First, an atom, usually a metal, gives up an electron. Metals are natural givers because they often have just one or two electrons in their outer shell, and ditching them is the easiest way to get stable. Then, as you see here, another atom, a taker, comes along and just snatches that electron. Nonmetals are fantastic takers because they're usually just one or two electrons away from having a full, stable shell. This transfer creates these oppositely charged ions that are now just irresistibly attracted to each other. And that powerful attraction is the ionic bond.
So let's do a real quick side-by-side. Covalent bonding, that's about sharing electrons, usually between nonmetals, like in a water molecule. Ionic bonding, that's about transferring electrons, usually between metals and nonmetals, and is what creates things like table salt, sodium chloride. See? Two totally different roads that lead to the exact same destination, stability.
So what about metals? I mean, what happens when it's just a bunch of metal atoms hanging out together? Well, they have their own, very unique strategy, and it's perfectly described by this amazing idea of an electron sea.
You see, in a chunk of metal, the atoms don't share electrons with just one neighbor, and they don't give them away completely either. Instead, all the metal atoms sort of donate their outer electrons to this giant mobile community pool. It creates a sea of electrons that can just flow freely around all the now positively charged metal ions.
And this electron sea idea, it explains perfectly why metals behave the way they do. You know, those mobile electrons that can move around? That's like a river of electrical charge, and it's exactly why metals are so good at conducting electricity. It's also why you can bend a paperclip or shape aluminum foil. The atoms can slide past each other inside that flexible sea of electrons without actually breaking the bond.
So here we are, right back where we started, looking at this incredibly complex molecule. But now we see it a little differently, right? We can see that it's all built from just a few simple rules. Atoms finding stability by either sharing, giving, or pooling their electrons. And from these really basic interactions, the infinite, amazing complexity of our world is built. So that's our look at chemical bonding, and it kind of leaves you with a final thought, doesn't it? If these simple rules of attraction can build everything we can see and everything we are, what other fundamental, invisible forces are out there shaping the world around you in every single moment? Thanks for tuning in.